All right, example 4. Determine the radius and interval of convergence for this power series. All right, so again, we're getting in the habit here of always immediately jumping to the ratio test. So for the ratio test, we can go ahead and there's a couple little things we can do here to save a little bit of time. If you're following along in these videos, in the previous videos, I've been explicitly writing out what a sub n and what a sub n plus 1 are. At this point, let's just fill in a sub n plus 1 over a sub n. And also, since the ratio test contains these absolute value bars, this negative 1 to the n component is just going to turn into 1. So I'm effectively just going to drop that and not write it at all because the absolute values will take care of it. So for a sub n plus 1, I'll fill this in. So this will be x minus 3 to the n plus 1 and 2 times n plus 1 plus 1. Divided by a sub n, we'll flip and multiply by this, so the reciprocal of that. So 2n plus 1 all over x minus 3 to the n. Closing that off, simplifying a bit more. So again, let's actually apply the absolute value bars to the pieces that do need it. So here we can break this x minus 3 to the n plus 1 up into x minus 3 to the n and x minus 3. In the bottom, though, we have got an x minus 3 to the n, so those cancel, and we're left with just this x minus 3 to the n. But instead of using parentheses, the absolute value bars do apply to that. The absolute value bars do apply to this, but because this is a positive number, it just can be left as 2n plus 1. Downstairs, similarly, we don't need the absolute values on that term, so we can just distribute the 2 and combine like terms to get 2n plus 3. We can also factor out the x minus 3 since the limit is only concerned with terms that contain an n. So the limit as n goes to infinity times that absolute x minus 3 of 2n plus 1 over 2n plus 3. This limit here is the ratio of the leading coefficients, 2 over 2, which is 1. So here we get rho is equal to absolute x minus 3, and we would have convergence if this is less than 1. So this tells us the radius of convergence is 1, and therefore, if we think of our number line here, our center of our power series, which is 3, we need to figure out what's going on at x equals 2 and at x equals 4. So at x equals 2, our power series turns into negative 1 to the n times a negative 1 to the n over 2n plus 1. Now these two negative 1 to the n's will combine to give us a negative 1 to the 2n, which is really a 1 to the n, which is 1. So we really end up having just 1 over 2n plus 1. And we can compare this to 1 over n using the limit comparison test. And we'll get divergence because this series here is the excuse me, the harmonic series which diverges. So this diverges. And I'll say by LCT with b sub n equals 1 over n, if you want to go through that. X equals 4, rinse and repeat. We'll have negative 1 to the n over 2n plus 1 if we plug that in, because here we'll get a 4 minus 3, which is 1 to the n, which is 1. We'll keep this, and we'll keep that. This is a alternating variety of a harmonic series, harmonic-like series. The alternating harmonic series converges, so we're led to believe that this variant should also converge. We can show that this does converge by the alternating series test. And for alternating series, we have to say what our sequence is. So the positive part of the sequence would be 1 over 2n plus 1, and this b sub n definitely is positive, is decreasing, and converges to 0, which are the 3 necessary hypotheses for convergence. So we have converges here. So ultimately, back up here in our interval, we are going to exclude x equals 2 because we found that it diverged there, but we are going to include x equals 4 because we found it converges there. So I'll make that a solid circle. And there is our little diagram, very much like middle school algebra, but it does communicate what the interval is quite clearly. The interval of convergence I is open on 2, but inclusive or closed on 4. So it's the half open interval from 2 to 4.